Hello, I am Mrs. Edwards, and today we're going to go over the rational root theorem. But before we go over the rational root theorem, I want to help you understand why we need the rational root theorem. And then eventually we'll use it to factor some polynomials. So here I'm starting with a polynomial because the rational root theorem only works on polynomials. Okay, and then I'm going to graph it. Okay, when you graph this cubic, we have these three x-intercepts. Now, x-intercepts always happen at either rational numbers or irrational numbers. It has to be one of those two kinds of numbers. Now, the rational root theorem is only going to find all of the places where the function crosses the x-axis at a rational number. It is not going to find directly where it crosses at the irrational numbers. Currently, when we're thinking, where does this cubic cross the x-axis? Well, currently there are an infinite number of possible numbers where this graph crosses. So the first thing that the rational root theorem does for you is it gives you a relatively short list of possible places where this function crosses the x-axis. Okay, so it's going to start by finding potential rational roots, in other words, zeros. Okay, after we have this relatively short list of possible places where the function might cross the x-axis at a rational number, we can then use the remainder theorem to decide which one or ones of these possible places actually are indeed x-intercepts. So we'll find the actual ones that work. Now, in this particular case, the only rational root is -1. And then these other two x-intercepts don't end up being rational numbers. So when we use the rational root theorem, it would not reveal anything other than -1 because it's only going to give me all of the actual rational roots. Okay, but then we can use that rational root to find the irrational ones. And in this case, these are our two irrational roots. Once we have all of our roots, we're going to be able to factor the original polynomial, in this case f of x, into a product of linear factors. So if you have a polynomial of degree 3, then for sure you're going to be able to write it as a product of 3 linear factors. So degree 3 will have 3 linear factors. Now in today's lesson, we're only going to be concerned with roots that are rational and irrational. Later we will have some complex roots, but we're going to save that for another day. So if we do factor this polynomial, x minus the root, or x minus the 0, is a factor. So in this case, that's what we would have as our factored version of f of x. I want to say one more time, because I feel like students kind of get confused on rational versus irrational, so we're going to take a moment to remind you of what those mean. Okay, so rational numbers, ratio, the root word is ratio. A ratio is a fraction. All rational numbers can be written as a fraction. Now, the fraction isn't obvious, always obvious. Like the number 5 can be written as 5 over 1, so it's rational. 0.7 is 7/10, so 0.7 is a rational number. 0.3 repeating can be written as the fraction 1/3. So another way to think of what is rational and what is irrational is to think of first just what's irrational, and anything that is not irrational is rational. So irrational numbers, they are decimals that go forever but without a pattern. So again, 0.4 repeating is the fraction 4/9, so it is not an irrational number. Irrational numbers are only decimals that go forever without a pattern. Some examples, obviously these two that we just found, but the square root of 2 is an irrational number. Pi is an irrational number. E is an irrational number. Okay, so decimals that go on forever without a pattern. But all x-intercepts are either rational numbers or irrational numbers. And the theorem that we're starting with here, the rational root theorem, is only going to find the x-intercepts that are rational numbers. If I were to use something like Desmos, just be careful because notice -3 plus 2 root 7 all over 4 is approximately 0.686. But this is a rounded version of a decimal that goes on forever without a pattern. Okay, so this one is irrational, and same thing here. That -2.186 is a rounded version of this decimal. So these two are irrational, and -1 obviously rational. Okay, we're going to use the rational root theorem here in a minute, but let's just quickly go over the mechanics of the rational root theorem. So you start off with a polynomial, a number x to a power plus a number x to a power. We've talked at length what a polynomial is. Okay, and then the number that is in the front, that leading coefficient, that is going to be how you generate the variable q. And then how you're going to generate the p-values, that comes from the number at the end. So to help you remember that, just silly story here. Well, the queen, always comes first. And then the poor peasants, they're always last. Okay, so Q, number in the front, P, number in the back. Now, the potential rational zeros, the potential rational roots, they are created by making fractions of P over Q. Okay, so how are you going to remember that it's P over Q? Well, like any good story, the peasants rise up over the queen and overthrow. Ooh, this is kind of a spicy story. All right, so here are the peasants. They arm themselves. Ooh, danger, danger. They rise up over the poor queen, poor queenie. Kind of looks like they're stomping her. Sorry, that's a little graphic. Okay, but you're making fractions P over Q. Now, specifically, the P is every factor of the number here at the end, and the Q's are every factor of the number in the front. Now, they are plus or minus, because if you had the number 6, 1 times 6 is 6, but so is -1 times -6. When we look at a specific example, all of that will become clear. But from this, what you really need to take away is the number in the front creates your Q's. Queen comes first. Number in the back is known as P, and all the factors of it are P. And that comes in the back because those are the peasants. And then the fractions are peasants over queen. So hopefully the little trick there is going to help you remember where the P and the Q are, so that you can get your list of possible rational zeros. So starting here, Q, queen comes first, and P, peasants at the end. Now when we actually list these out, Q is actually plus or minus every factor of 2. All right, so the only factors of 2 are 1 times 2, so we get plus or minus 1 and plus or minus 2. All right, for P, it's every factor of 6, positive and negative. So 1 times 6 is 6, and 2 times 3 is 6. So my P values are plus or minus 1, 2, 3, and 6. All right, now the possible rational zeros, we create those by making fractions of P over Q. The peasants rise up over the queen. Poor little queenie. All right, so P over Q. You want to be very systematic about this. You don't want to just randomly start pairing numbers, so I'm going to start with p, this first p, 1 over 1, 1 over 2. Okay, moving on to the next p-value, 2. So 2 over 1, 2 over 2. Then moving on, 3. So 3 over 1, 3 over 2. And lastly, 6 over 1, 6 over 2. We do not have our complete list. We want to simplify, get rid of any duplicates, and they are all plus or minus. All right, so here's my final list. Let's look back up here how I got that. 1 over 1 is 1. 1 over 2 is 1/2. 2 over 1 is 2. 2 over 2 is equal to 1. That's a duplicate, and you don't want to write duplicates. So that one gets left off. 3 over 1 is 3. 3 over 2 is 3/2. 6 over 1 is 6. 6 over 2 simplifies to 3, and we already have listed 3. So here is the complete list of potential rational zeros. Okay, again, what does that mean? These are all the places the cubic function might cross the x-axis, but specifically only the places that are rational numbers. You can have x-intercepts that are rational or irrational. So this is a list of every possible rational one. Next, we need to figure out which ones are actually x-intercepts, which ones are actual zeros. So what we're going to do is we're going to use our remainder theorem, which is what we did last lesson. And the remainder theorem is you take the number, you substitute it into the function, and see if it equals 0. If it is, well then, the consequence is it's a factor, which is the factor theorem. Okay, so we're going to find those actual zeros by substituting every number in this list into the function. And I know you're like, wait, that short list doesn't look so short anymore. But it is relatively short compared to every possible number on the number line. All right, so let's get it out. I substitute in 1. 2 times 1 cubed plus 1 squared minus 13 times 1 plus 6. That equals -4. Nope, not a 0. I plug in -1. 2 times -1 cubed plus -1 squared minus 13 times -1 plus 6 is 18. Nope, sorry. I substitute 1/2. 2 times 1/2 cubed plus 1/2 squared minus 13 times 1/2 plus 6 is, victory, 0. Okay, so I continue doing this. I substitute in -1/2. I substitute in 2, victory, because it equals 0. I plug in -2, I plug in 3, and I plug in -3, and I get 0. Now I realize that I have not substituted every single number off of this list. But remember, if this is a cubic, well then the most you can have is 3. If this was a 4th degree polynomial, well then the most zeros you could have would be 4. So we've already found 3, so I can stop substituting. I don't know, I couldn't help myself, so there we go. I substituted the rest of them just in case maybe you paused and you substituted to try to figure it out on your own. Okay, so we have our actual zeros now. Now remember, these are only the rational ones. If we were to graph, we could graph the function even with this information because we have our x-intercepts at 1/2, 2, and -3. There's one of each one, so the multiplicity is 1. We have a cubic with a cubic with a positive leading coefficient, so we know the end behavior starts down and ends up. And because there's only one of each, we're going to slice, we're going to slice, and we're going to slice, and we could even graph. You will not have to do that on your homework, but that's a good review of what we've done earlier in this chapter. Okay, now I said you can then use the rational roots to find the irrational ones. But in this case, again, because it was 3rd degree and we already found 3, we already know that there are not any irrational roots. So we have, if the follow-up question was, name the rational and irrational roots, I'd say, well, the rational ones are 1/2, 2, and -3, and the irrational ones, none. We don't have any. All right, so here we go. Let's list those potential rational zeros. Oh, Queenie, she comes first, peasants at the end. So the Q, all the factors of 3. 1 times 3 is 3, so we just have 1 and 3. And then all the factors of 8, 1 times 8 is 8, 2 times 4 is 8, so we have plus or minus 1, 2, 4, and 8. The possible rational zeros, we make that list by creating fractions of P over Q. The peasants rise up over the queen. Da, 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 da. Poor little Queenie. Okay, be very systematic when you make this list. So I'm going to start with 1 right here, put it over 1 and 1 over 3. Then move on to 2, 2 over 1, 2 over 3, and so forth. Okay, so I have my list. And then this is not my complete list of rational zeros. I have plus or minus, and I want to simplify. So we end up with that list of numbers. Okay, now that we have a list of our potential rational zeros, we have to figure out which ones actually work. Now, in your calculator, one thing, just as a recommendation, is if you put each of these numbers, you want to put it inside parentheses. So when you type this in, because you are substituting each one of these numbers, as painful as it is, into the function. So you could go 3, and then you have a set of parentheses, the 1, and then to the third power, plus 2, and inside the set of parentheses, the number 1, to the second power, minus 25, inside parentheses, the number 1, plus 8, enter, and you get negative 12. Now, if you set it up this way, then you could go back and edit rather than redo. Now, if you're going to put in negative 1, another handy feature to know about your calculator is the button Insert. It's usually right there by the delete, because if you start typing, it types over the top of it, and you need more space. So when you type in negative, it goes over the top of 1, for example, but then use Insert 1, and then you can finish editing that line and hit Enter, and then that will go a little bit faster. Okay, but nonetheless, it is long. So here we go. I plug in negative 1 into the function. I plug in 1/3, and we're like, yes, oh my gosh, we got a 0. Remember, we're hoping for 3. If we can find 3 numbers that are zeros, then we don't have to substitute any more numbers. Okay, I plug in negative 1/3, and I get 16.4 repeating. I plug in 2. Again, it's like 3 times 2 cubed plus 2 times 2 squared minus 25 times 2 plus 8, and I get negative 10. I continue substituting. Oh, I'm not finding any. Oh, no. Oh, that was so painful. Okay, so we have substituted every possible potential, every potential rational zero. And we only found one of them that worked. This is a cubic. So what that means is the other 2 x-intercepts are not rational numbers, they are irrational numbers. But we're going to be able to use this rational zero to find the irrational ones. Kind of spoiler alert, I know, but I went ahead and just made a sketch so you can have a visual of what just happened. Here is where the 1/3 is. This graph is crossing at 1/3. These 2 places where the cubic is crossing, this is not a rational number. It's a rounded decimal version of an irrational number, and we've got a couple of those. Okay, so we're going to be after those other 2 zeros. All right, so we used the P over Q and found that the 0, 1/3. So far, if we were listing the zeros, the rational zero is 1/3, and that is the only rational zero we have. We need to find these irrational zeros. Okay, so right now, we don't know what they are. So the next thing we want to do is use this 0 to write a factor of the polynomial, which starts by saying x minus 1/3. Danger, danger, this is not 1/3, right? We have to, this is an intermediate step. So multiply through by 3 because of that 3, and we end up with 3x minus 1. Okay, and we will eventually have two more linear factors, but we know at least from this 0 here being 1/3, we know one of the factors is 3x minus 1. Okay, well, if you know a factor of a number, you can find another factor by dividing by the one you know. So what we're going to do is I'm going to come over here, and I have to scooch myself over. I'm just going to move myself there. And we're going to divide the original cubic by the factor 3x minus 1. We cannot, in this particular instance, use synthetic division because we are not dividing by something of the form x minus k. Now, on the assignment, if it turns out that your 0 was 7, well, then you could synthetically divide to find your answer. Okay, but in this case, I can't. I'm going to have to go with long division. So to figure out what number goes up here, it's what's in front over what's in front. So 3x cubed over 3x simplifies to x squared. Then you take this and multiply it times everything out to the side. So x squared times 3x is 3x cubed. X squared times -1 is minus x squared. Draw my line and subtract. So I want to run a negative all the way through, combine, and we get 3x squared. We're going to bring down that minus 25x and start again. So to decide what number goes up here, we have 3x squared over 3x. So 3x squared over 3x is just x. Then multiply times everything. So x times 3x, 3x squared, x times -1, minus x. Draw my line, subtract, running a negative through, and I end up getting -24x. Bring that plus 8 down and start again. So to decide what goes up here, -24x over 3x is -8x, or excuse me, just -8. And then -8 multiplied out here, -8 times 3x, -24x, -8 times -1 is 8. Draw my line, subtract. No surprise, we know we have a remainder 0, which is how we came up with that 1/3 to begin with. But what we now know is this cubic is equal to 3x minus 1 multiplied by x squared plus x minus 8. Okay, so I'm going to come over here and I'm going to replace that. Okay, now x squared plus x minus 8 does not factor in that traditional sense, but we can figure out the zeros. Where does it equal 0? Now, obviously, we already took 3x minus 1 and set it equal to 0 to get a third. Like, that's where it came from. So I'm just focused on that one right there. So I need to solve that to figure out what those other two x-intercepts are. So to solve, I set it equal to 0, and in this case, I needed to use the quadratic formula, and it turns out I get -1 plus root 33 over 2 and -1 minus root 33 over 2. -1 minus root 33 over 2 is approximately -3.372, and -1 plus root 33 over 2 is approximately 2.372. Again, these are rounded versions of those numbers, which are irrational. So we've now found the other two irrational roots. There they are. Okay, and so we have 3 roots, and now we can rewrite this as a product of linear factors, x minus each of the roots. The first one amounted to 3x minus 1, and then I'm going to just pop in those 2 that we just found, and we have f of x factored. Now, it's just fine to leave it like this. That answer is perfect, okay, but if you are tempted, if you do change this to a plus, like you want to distribute, then run the negative through the numerator and that would become a plus. So you could, if you wanted, write the factored version as x plus, as long as you made this +1 minus root 33 all over 2, because a negative on a fraction can be with the top, with the bottom, or out to the side. And so currently it's out to the side. And if you did the same thing here, this would be plus when I run the negative through, and it would be +1 plus root 33 all over 2. Okay, but this answer is just fine. Usually put those irrational roots inside of parentheses if you don't want to run the negative through. To summarize, Rational root theorem. It allows you to find a list, a relatively short list of possible places that your function is crossing the x-axis, but the only numbers you're finding are the rational numbers where your graph is crossing. Then, now that you have a short list using that p over q, you take each one of those numbers and substitute them into the function to see if they equal 0. And if it equals 0, then you have found an actual rational root. Now, if you had a degree 5 function and you found 5 of these possibilities that work, you would be done because you would have all 5 and you wouldn't need to find any irrational ones. Okay, but you found the ones that actually work, and if you have the same amount as you do the degree, you have everything you need to factor, and you definitely don't have any irrational roots. But if you have a degree 3 and you only found one that worked, you need to take that and use x minus that number to create a factor. And then once you have a factor, you're going to divide it into the original function, and that's going to lead to finding your irrational ones. You'll come up with a separate equation that you can solve using possibly the quadratic formula, and then you'll have all of your roots, which you can use to factor. X minus each one of those roots is one of the linear factors, allowing you to rewrite the function as a product of linear factors. Whew! All right. Go and overthrow the queen so that you can factor those polynomials.